Welcome to lesson number 11. Previously, we implemented our sigmoid function on random sets of data to predict their probability values relative to some linear model. We then stopped and posed ourselves this question. How does the computer specifically determine which linear model better classifies our data? This is where we shift our discussion over to cross-entropy. Let's look at these two diagrams in a probability perspective. The best model is the one that gives the higher probabilities for the points that we know should be in the positive region, and the lowest probabilities to the points that we know should be in the negative. And we've already tested this person. They're labeled blue, and thus they should be in the positive. But according to our linear model, this point here is in the negative region since its probability is under 0.5. And anyone that's red, suppose we've tested all of them and we know they're diabetic. Yet this linear model predicts that this point is 80% in the positive, 80% likely of it being healthy, which is also wrong. Clearly this model better classifies our data since it assigns the higher probabilities to the points we know should be in the positive and the lowest probability to the points we know should be in the negative. For the computer to determine that this model has a smaller error than this one, let's make use of cross-entropy. What we need to do first is calculate the probability of the points being what they actually are. All of these probabilities correspond to the likeliness of something being blue, of being in the positive. For the red points, we need to determine their probabilities of them being red, not blue. And since probabilities add up to 1, their likeliness of being red, of being in the negative, is simply 1 minus the probability of it being blue. On the left-hand side, one of our red points, according to the linear model, is only 20% likely of being red. Which doesn't make any sense. We know this point is red, we already labeled it as such. But according to the linear model, it predicts that it's unlikely for this point to be red. The second diagram makes a lot more sense. All the red points are more likely to be red, all the blue points are more likely to be blue. They are classified correctly. This diagram we know has a much larger error than the second one, and given how we computed the probabilities, the error can be written as the summation of the natural logarithm of each probability. Let's apply this equation to both our diagrams. We get a negative number for both, which makes sense since the log of a number between 0 and 1 results in a negative value. And we're just adding negatives onto negatives, so what we'll do is reverse the sign by taking the negative of our summation. Looking at the results, it's clear that this model has a much larger error. This summation of logarithms is what we'll refer to as cross-entropy. This is a very important concept. When points are correctly classified, they have small error penalties, whereas when points are incorrectly classified, they have big error penalties. It follows that the linear model that better classifies the points is going to result in a low cross-entropy, and a bad model that incorrectly classifies its points has a large cross-entropy value. This gives us a method of determining a good model from a bad model by simply calculating the model's cross-entropy. Let's make this into an actual formula which we can then use in our code in the next video. The general equation for cross-entropy is the following, where P is the probability of a point being blue, and the variable y corresponds to a label of either 0 or 1. If our point is labeled blue, if we tested this person and they are healthy, it will have a label of 1. If our point is red, y will equal 0. This makes sense with what we've done so far, because think about it. Take this point, for example, that's blue. It has a label of 1 and a probability of 0.95, giving you 1 times ln of 0.95. And now the second term cancels out because 1 minus 1 is 0. And remember, for the red points, before putting them into the cross-entropy equation, we need to determine their probabilities of being red, not blue. And since probabilities add up to 1, the probability of the red point being red is simply 1 minus p of blue, which makes sense for this equation. Let's compute it for this point, the one that's 43% likely of being blue. And now since the red point would have a label of 0, the first term cancels out, and you're left with 1 times the ln of the probability of it being red. And if we keep doing that for every point, notice we get the same results as before. Except now, this general equation that we derived, we can actually use it into our code. That's our official equation for cross-entropy. And by convention, when computing the error function, we consider the average, not the sum, which is why we divide by the total number of points m in the end. Even if we were to take the average, it's still apparent that the first linear model has a much bigger cross-entropy than the second one, and therefore a much larger error. This sets us up for gradient descent, since now we're able to actually calculate the error with cross-entropy. Subsequently, what gradient descent will do is keep minimizing the error and obtain a linear model. Before moving on to gradient descent, in the next lesson we'll go back to our code, pick a random model to represent our data, and calculate its cross-entropy.